let's take a look at the oxidation of the side chain of benzene. One of the things we do know is that the carbon that bonds to benzene, if it actually is also bonded to one hydrogen, then one of the product that is produced when you add potassium manganate as an oxidizing agent, you will actually end up with benzoic acid. So consistently, you can see all these compounds down here, because this C has a hydrogen that's bonded to it, and the carbon also bonds to benzene, you will end up with actually a carboxylic acid. Similarly, in the same vein, for the case of your ethyl benzene, and also same for the compound that's indicated down here. So this carbon that's bonded to benzene actually also is bonded to 2 hydrogen. Okay. So when that reactions take place, you find that what happens is that the KMNO4 will actually be decolorized and used up. It's important to take note of the 2 points that's indicated down here. So first is that potassium dichromate is not strong enough as an oxidizing agent to be able to oxidize this alkyl benzene to produce your benzoic acid. The second point is that if you have a structure as such, whereby this carbon is locked by another 3C, like I mentioned earlier, if the carbon that immediately bonds to benzene does not bond to any hydrogen, then in that case, there will be no oxidation. So another observation made is that in some of the reactions, you'll be able to observe effervescence because your carbon dioxide is actually produced. Another important thing to note is that when you use concentrated acidified KMNO4, you may actually produce carbon dioxide, which means in terms of a QA observation, you will get effervescence. So you can see that in this reaction, you get effervescence, and in these reactions, you get effervescence. Why? The reason is because that this carbon will actually oxidize to become benzoic acid, and clearly adjacent to it and clearly bonded to it, there's also another carbon that's bonded to it. So as a consequence, that this structure will now be converted to actually benzoic acid. Whatever remaining carbon will now become carbon dioxide. Similarly, in the same vein, you will see that this structure down here will now go ahead to become this. And this is where your carboxylic acid is. That means that the 2CH3 that's down here can only end up becoming carbon dioxide, which helps us to explain why in this reaction there's actually 2 mole of carbon dioxide that's been produced, because there's actually 2 methyl group bonded to this carbon that becomes COOH. The final point to add is to take note that KMNO4 can be acidic or it can be alkaline. If it's alkaline, all the benzoic acid, as you can see, will become benzoate. And do note that benzoic acid is partially soluble in water, and it will form a white PPT. But if it becomes a benzoate ion, then it can form ion dipole attraction forces with water molecule, which means it becomes absolutely soluble and you get a colorless solution. So you can see it down here. Okay, finally, if you were to use alkaline KMNO4, there will also not be any carbon dioxide produced and no effervescence will be observed. The reason is because that your CO2, which is an acidic oxide, would actually react with OH minus. Okay, and that will give you your HCO3 minus.